All right, I'd like to get started. Today I want to talk about virtual machines. And the lecture is really going to be divided into three pieces. One is I'm going to start with what's called trap and emulate virtualization, which is basically an overview of how you could build your own virtual machine scheme on RISC-V in QEMU. Then I'm going to talk a bit about recent hardware support in microprocessors for virtualization. And then about today's paper, Dune, which uses this modern hardware support. All right, so first, what's a virtual machine? It's really, you can think of it as a simulation of a computer that's accurate enough to run an operating system. So QEMU is a example of, you could consider to be an example of a virtual machine. The way I'm going to talk about it is that down at the sort of the lowest level, sitting on top of the hardware, we're going to imagine a virtual machine monitor, or VMM. And this more or less takes the place of a standard operating system kernel. And the virtual machine monitor's job is to simulate a bunch of computers for guest operating systems. So, up here in what used to be user space in our usual diagrams, but is now guest space. So this is, I'm going to call this guest space, and down here, host space. We're going to have a bunch of one or more guest operating systems, kernels. So we might have a Linux kernel as one guest. And this Linux kernel is going to, it's just it thinks of itself as an ordinary kernel, and it runs a bunch of processes, maybe a VI and a C compiler. And we might have other guest, guest virtual machines running here. That might be maybe another Linux, or maybe even some other operating system like Windows, all running on the same machine. And there would be Windows processes running within this guest operating system. So we have the host world where the virtual machine monitor runs, and the guest world where these ordinary operating systems run. And furthermore, we're going to talk about a lot about within the guest world, guest supervisor mode, which is the mode that the kernels run in, the guest kernels run in, and guest user mode. And again, the kind of classical goal of the virtual machine monitor is to provide an emulation of a machine that's so good that you can just boot ordinary Linux or ordinary Windows unmodified and have it run inside this virtual machine, never suspecting that anything funny is going on. So, for example, the virtual machine monitor has to be in a position to emulate the difference between supervisor mode and user mode in a way that is just completely convincing simulation of how the actual hardware does it, even though that's, can't really be exactly what's going on. So that's why we talk about guest supervisor mode and guest user mode. These are the VMM's emulation of those two modes. So why would you want to use a virtual machine? It turns out there's a lot of reasons to run lots of distinct guest operating systems on a single computer. Sometimes, maybe you're running a big company, and you need to have lots and lots of servers, maybe name servers and security servers, who knows what. And each one of them doesn't use many resources, so it's sort of a waste of time to have to buy a physical machine for it. But you want to run, you want to run lots of these low-intensity servers on a single piece of hardware. So you can save money by using a virtual machine. It turns out virtual machines are also very widely used in cloud computing, where it's an outfit like Amazon AWS. They don't want to rent out physical machines to people, because that turns out to be difficult to manage. What they want to do is rent their customers, their cloud customers, just a machine that Amazon can, on the fly, decide what hardware to run it on, whether to run it on a bigger or smaller machine. Amazon can decide, its current customers, maybe it has 2 customers on this piece of hardware right here, but they're not using the computer very much. Maybe it can pack a 3rd or a 4th customer on to that same piece of hardware, without spending extra money, but get more revenue. So this virtual machines allow kind of extra level of flexibility. And it's the kind of trick that's being used is that we're kind of shifting up the existing operating system kernels in user space and adding a new layer underneath to provide this flexibility. It turns out there's other reasons why people use virtual machines. One is certainly kernel development, which is why we all use QEMU. The ability to run XV6 in a kind of virtual environment rather than on a real computer makes this course much more convenient for all of us. It also makes it a little bit easier to debug, because turns out that once you're running XV6 in this virtual machine environment that QEMU provides, it's easier to provide GDB access than it would be on a physical computer. And a final reason that people use virtual machines is that there's a bunch of tricks that can be played using this extra layer of indirection provided by the virtual machine monitor. For example, you can checkpoint an entire running operating system and user processes. You can take a checkpoint of it, stash it away somewhere, maybe on disk, and then later restore that checkpoint, sort of exactly the state of that operating system and its processes as it was at the time of the checkpoint. And it's useful for reliability, for debugging, for maybe cloning the image of a virtual machine so you can run it multiple times. Another game you can play is you can migrate an entire guest to another computer. If you have a guest operating system running on a physical computer and you need to shut down or replace that physical computer, you can actually, turns out, move the running virtual machine image without disturbing it to another physical computer so that you can shut down the first one. So there's just examples of why people really like virtual machines. And people really do. Virtual machines are very, very widely used. And they also have a long history. This ideas first came up in the 1960s, and they've been developed over time until they're quite pervasive and easy to use. For this course, the reason why we're looking into them is that virtual machine monitors provide a sort of different view on what an operating system can be. Instead of the process abstraction we're all used to, we have some analogous structures here, but we're providing a different kind of container. It's not a process, it's a sort of simulated machine. So it allows us to kind of think about all the stuff we've been talking about, memory allocation, scheduling, protection, from a different point of view. And maybe give us some ideas which we can take back to traditional operating system kernels. And indeed, much of the action, the sort of design, development, research action has shifted from conventional kernels down into the virtual machine monitors themselves as they've gotten more and more prevalent. So in some sense, kind of the topic of operating systems is drifting downwards a bit by one layer. Okay. For the first part of this lecture, I want to talk about a bit about how we could implement our own virtual machine. And I'm going to use RISC-V as the sort of assume that we're trying to emulate RISC-V hardware so we can run operating systems that's designed for RISC-V, like XV6. And just to repeat the specific goals, what we'd like, for kind of classical virtual machines, what we'd like to build is something in which the guest software is just completely not aware that it's running inside a virtual machine. We want to build something that makes it impossible for the guest software to distinguish, to decide whether am I running on a real machine or a virtual machine, right? We want the emulation to be that good. And the reason for that is that we don't want, we want to be able to run, we'd like to be able to run anything in our virtual machine, any operating system, even maybe an operating system we haven't heard of. And that means that, whatever funny stuff the operating system does in the way it uses hardware, the virtual machine has to provide that, an emulation of exactly the hardware, so that any tricks that work on the real hardware are also going to work in the virtual machine. A sort of similar goal that we'd like is we want there to be no way, not only no way for a guest to decide if it's running on a virtual machine, but no way for a guest to be able to escape from the virtual machine. A lot of the reason why people use virtual machines is to provide strict confinement for untrusted software, even untrusted operating systems running inside the virtual machine. For example, if you're Amazon and you're selling cloud service, and it's your customers often who provide the operating system that runs in the virtual machine as well as the applications. And gosh, for all you know, your customers are not running ordinary Linux. They're running a special hacked version of Linux who's intended to try to break out of its virtual machine and break into Amazon's, either the virtual machines of Amazon's other customers or into the virtual machine monitor that Amazon uses to enforce isolation. So it's quite important that guests not be able to break out of their virtual machines, that they be able to use the memory that they're allowed to use by the virtual machine monitor, for example, but not other memory. And similarly, that they shouldn't be able to reach out without permission and use things like storage devices or network interface cards. So we want to have very strict isolation. And in many ways, virtual machines provide stricter isolation than ordinary Unix processes. Ordinary Unix processes can often interact, they can kill each other, or they can all read and write the same files or communicate over pipes. But in a sort of ordinary virtual machine system, none of that's possible. In the different virtual machines running on the same computer are just completely isolated from each other by the virtual machine monitor. So people like them for security, right? It's a way of being able to run untrusted software without having to worry if it's buggy or malicious. Now in practice, I've pitched the goal as being a sort of completely faithful emulation of a physical machine. In fact, it turns out that for performance reasons, this is often blurred. And you'll find, for example, that Linux and the most common virtual machine monitors have co-evolved a little bit, so that in real life, Linux may actually be aware that it's running on a virtual machine monitor, and with the virtual machine monitor's permission for efficiency, Linux sometimes knowingly talks down to the virtual machine monitors to do things like get high-speed access to devices. But that's a carefully controlled exception, and the general strategy is completely faithful simulation. Okay, so how could we build our own virtual machine monitor? Well, one possibility would be to do it entirely in software. You can imagine writing something like QEMU that interpreted the machine instructions. That is, you could write a program that would open up the XV6, read the file that has the XV6 instructions in it, and your program could look at each instruction and say, oh, that's a load instruction or a move instruction, and your program could sort of simulate RISC-V state, like it might have 32 registers implemented in software. And as your software sort of reads each instruction and picks it apart and figures out what kind of instruction it is, it would apply the effects of that instruction to the 32 registers and control registers that it was simulating, all in software. People do this, and it's conceptually straightforward to make it work, although it may be a lot of work to get all the details right. The reason why sort of pure software interpretive virtual machines aren't widely used is that they're slow. If you play this game, your virtual machine is going to run guest software at a small fraction of the speed of the hardware that you're using, because for every if your virtual machine monitor software has to look at every instruction as it's executed up here, your machine monitor is going to maybe run dozens of instructions in the process of interpreting each one of the guest instructions. And so it's going to be orders of magnitude slower than a real computer. And for something like cloud computing, it really would not be practical. So people don't use the software interpretation to build virtual machines for production systems. Instead, the sort of core of one of the main widely used strategies is to actually run the guest instructions on the real CPU. So if you were going to run XV6 in your virtual machine monitor, you would actually load XV6's instructions, the kernel, the beginning, the entire XV6 instructions in a memory, and then jump to the first instruction in XV6, right? In order to have your computer actually run the instructions in XV6. And of course, this requires that your computer have the same microprocessor in it that XV6 is expecting, but that's easy to arrange. Now, it turns out you can't literally do this. The point at which you would run into trouble is when your guest operating system first executed a privileged instruction, right? If it, and that's really the difference between a kernel and ordinary user code, is that kernels, which is what we're trying to run here in our virtual machine, kernels use privileged instructions. So your guest kernel might, for example, try to load a new page table into the SAT-P register on RISC-V. And so that's starting to present a puzzle. If we're executing our guest kernel as an ordinary user process in Linux, for example, boy, loading SAT-P is an illegal instruction in user mode. And so our program's going to crash. If we are so foolish as to load our guest kernel into and run it in supervisor mode somehow, then our guest kernel will now be able to modify the real page table and would be able to escape from its virtual machine, and because it can control the contents of PTEs, read and write any memory. So we can't use a strategy that's as simple as just running the guest kernel directly. Instead, we're going to start playing some tricks. The first step is to run the guest kernel in user mode. So this is sort of the fundamental strategy here. We're going to run the guest kernel in user mode. In the RISC-V user mode. And so what that means, we're writing our own virtual machine monitor. And when we tell it, look, please boot XV6, it's going to load XV6's kernel instructions into memory somewhere. Maybe set up a page table appropriately that makes it look to XV6 like its memory starts at 0 and goes up to whatever high memory is. And then the virtual machine monitor will use a trap, SRED instruction, as you've all come across in XV6, to jump into the first instruction of the guest OS in user mode. And so the guest operating system will execute along. And now many instructions will work fine if the guest operating system is just adding two registers together, or even loading or storing from memory. That'll just work. And as soon as the guest operating system uses privileged instruction, what's going to happen is it's going to trap the RISC-V hardware. We'll cause it, since it's running in user mode, not supervisor mode, we'll cause it to trap back into our virtual machine monitor, and we'll get control. So if the guest operating system, for example, tries to change SAT-P, the page table pointer, boom, the RISC-V CPU will trap into our virtual machine monitor, and our software will get control back. And our software will be able to look and see what instruction caused the trap and do something appropriate. But the cool thing here is that the guest operating system didn't actually get to set the page table pointer.
But how does the VMM intercept this? Like, it has to set the trap handler, right? Isn't that something only a privileged process can do?
That's
like
right.
The VMM is a user program on the host OS, right?
Okay. What I'm assuming is that the virtual machine monitor runs in supervisor mode. So in this simple picture, the virtual machine monitor is the kernel that boots on this piece of hardware. So instead of booting Linux or whatever, you would boot this virtual machine monitor. It boots in supervisor mode. It has complete control over the hardware. And so we can set up, STVEC and all this other stuff, however it likes.
That makes sense.
Now, and actually some virtual machine monitors work at exactly that way. You just boot them on the hardware and it's just the virtual machine monitor only that's running in supervisor mode. In fact, there's also many, many virtual machine schemes out there. In fact, boot Linux. And then once Linux is up and running, you load the virtual, either Linux, actually Linux comes with a virtual machine monitor, or you load the virtual machine monitor as what's called a loadable kernel module into Linux, and it runs in the kernel in supervisor mode. And that's the way actually today's paper works, is you boot Linux and then run this loadable kernel module. But the main point is the virtual machine monitor software, the software we're writing that we trust, runs in supervisor mode, and we're going to run the guest in user mode, but arrange for it to look like it's running in supervisor mode as far as this is concerned. Okay, so the good news is that on RISC-V, everything dangerous traps if you try to do it in user mode. That is, all the sort of privileged things that supervisor mode can do, with the exception of stuff having to do with the page table or PTEs, which we'll talk about in a bit. But basically, every supervisor-only instruction causes a trap if you try to execute it in user mode. So that means that every time the guest operating system does anything like reads scause or reads and writes STVEC or does any of those things that XV6, for example, does to kind of configure the privileged part of RISC-V hardware, will cause a trap into the virtual machine monitor, and we'll get control. And then the game is going to be that the virtual machine monitor is going to maintain virtual state, a whole table of virtual state information for the guest. So the virtual machine monitor will have, for example, a virtual STVEC register just implemented as a variable in software, and a virtual SEPC register, and all these protected registers. There'll be a whole array of them down here implemented by the virtual machine monitor. And when the guest operating system, for example, runs the instruction that reads one of these registers, boom, it'll take a trap because it's not legal in user space. The virtual machine monitor will inspect the instruction and say, aha, that's an instruction that's reading the SEPC register. And so the virtual machine monitor will then emulate that instruction. It'll read the virtual SEPC value out of this array. It'll copy that into the hardware. What really happened here is that the I forget the name of there's some instruction whose name I forget, which is basically supervisor read, although that's not its name. And you give the name of an ordinary register and the name of a privileged register like SCPC. And so what that will trap, the virtual machine monitor will read that instruction. We'll see, oh, it's an S read. The virtual machine monitor will copy the virtual copy of SCPC into A0 in the trap frame. Because after all, when entering the VMM, that's going to have created a trap frame with copies of all the guest registers. It'll copy this SCPC into A0 in the trap frame, then return from the trap, using SRET. After copying the trap frame registers and the real registers, return from this trap to the instruction after the S read and continue reading there with now A0 set to the virtual SCPC. And now the guest operating system will proceed, not realizing that something funny happened here, but it will have gotten a copy of the virtual SCPC that the VMM was keeping on its behalf. So, any questions about this strategy?
How does the VMM differentiate between different guests?
It's basically the same way. It would keep one of these tables of virtual state per guest, and it just knows, just like XV6 knows which process it's running. It has a variable, maybe a per core variable saying, here's the process I'm currently running. Similarly, a VMM would have a per core variable that indicated which virtual machine, there'd be multiple of these state structures. The VMM would know which virtual machine it was executing, and it would look in the appropriate virtual machine state structure defined, SEPC or whatever it is it's looking for.
Can it run multiple, can it assign multiple cores to one of the guests?
Yeah, sophisticated virtual machine monitors can do that, yes. So if you, sorry, go ahead.
Oh, sorry. So the guest operating system, it will have like some registers in the actual hardware will be the registers that the guest OS uses. So why do we not use the actual SCPC, but use a virtual one?
The reason is that the virtual machine monitor needs to use these registers, needs to use the real registers. So for example, think about SCAWs. When a trap occurs, what happens on the when the guest operating system tries to do anything privileged, a trap will occur, and the hardware sets the real hardware SCAWs register to the cause of the trap, right? Which is illegal instruction or unprivileged instruction, whatever it is. But if the guest operating system, supposing the guest operating system has just taken a system call from a guest user process, the guest operating system needs to see an SCAWs that's whatever the right SCAWs value is for system call, right? Even though maybe the last thing that, so the guest operating system is going to read SCAWs, in the trap and what it thinks is the trap handler handling a system call from one of its guest processes. The SCAWs that the guest operating system needs to see is the value that means system call. But the SCAWs is going to be in the real SCAWs register is the SCAWs that means illegal instruction or unprivileged instructions violating the privilege rules. So there are actually some times when you could, well, anyway, in general, the VMM, the VMM is the one that needs to see the VMM needs to see different values in the real registers than the operating system should see in its vision of the registers. Does that make sense?
Thank you. Yeah.
All right. Okay. So this is called, the name for this style of virtual machine implementation in which the guest runs at user level and therefore traps whenever it tries to do anything privileged, and the VMM can emulate the privileged instruction. The name for that is trap and emulate. It's nice because you can build this for yourself. Actually, you can build this for yourselves entirely in software. You could modify XV6, for example, to be a virtual machine monitor on RISC-V and run little virtual machines, perhaps regular XV6, just by writing software. Of course, your software does have to run in supervisor mode. The state here, all the registers that begin with S, all those supervisor control registers, have to be part of this virtual state. There's also some other things that are not directly accessible from those S registers that nevertheless need to be down in this state. One of them is the mode. The virtual machine monitor needs to know whether the virtual machine is running in guest user mode or guest operating system mode. Because, for example, if user code executes a privileged instruction, like trying to read SCAWs, sure, that'll cause a trap into the VMM too. But in that case, the VMM should not just emulate the instruction in return, because that's not a legal instruction in user mode. So the VMM has to track whether the guest is in guest supervisor mode or guest user mode. And so there's going to be a mode slot down here as well. And the VMM will know because when the guest operating system jumps into user space, it'll execute the SRET instruction. SRET is a privileged instruction, and so the VMM will actually get control there and we'll see, oh, the guest is running an SRET instruction. Among other things, I'm going to change the virtual mode from supervisor to user. And another hidden piece of state is the heart number. That is the core number. You can't get that directly, even with a privileged instruction. But the VMM sort of needs to keep track of which heart it's emulating right now. Okay. The RISC-V, it turns out different CPUs are different levels of difficulty and how hard it is to write a trap and emulate virtual machine on them. The RISC-V is particularly well suited to it because the designers had that in mind when they were designing the instruction set. And so they knew what the requirements of a trap and emulate virtual machine were. And for example, they've been quite diligent in making sure that every single privileged thing that supervisor code can do will cause a trap if you try to do it in user mode, which is what you need in order to make sure the virtual machine monitor sees a trap for every privileged instruction.
I have a quick question. So does anything actually run in the guest OS itself, or does it always trap into the virtual machine monitor?
All ordinary instructions, like if you just have an add instruction that adds, I don't know how to write this RISC-V assembly, but let's just say you add A0 to A1 and you want to put the result in A2. That instruction just executes directly on the hardware at full hardware speed. If you make a function call, just an ordinary function call up here in the guest world, that just executes without anything special. It's just an ordinary, all the instructions that are legal in user code, all non-privileged instructions just execute directly at full speed when the guest operating system executes them. Okay, so is there a semblance of like user mode and kernel mode in the guest OS? Yes, the guest operating system is, well, the guest operating system is unchanged. So what we're running up here is exactly the Linux kernel or exactly the XV6 kernel. And of course, XV6 has all, it knows, the XV6 kernel knows it's running in supervisor mode. Yeah. Right, it just is. Of course, it's not here, but as far as the code is concerned, it's just definitely running in supervisor mode. It just does all kinds of privileged things and expects them to work. And then it knows when it executes an SRET to get into user space, it knows, aha, I'm going to enter user space now. And the VMM sort of makes everything look like that's indeed what's happening. Okay. Okay. Even though it's actually in the real machine, it's in user mode in both places. But this looks just like supervisor mode, and this looks just like user mode. Okay. Cool. Okay. Okay, so when the so for example, when we execute SRET to enter user space, the SRET's privileged, luckily. It traps into the virtual machine monitor. The virtual machine monitor changes the virtual mode to user, even though of course the real mode is still supervisor because we're still executing down here. Changes the virtual mode to user. Just before it returns from the trap, the virtual machine monitor sets the real SCPC to the virtual SCPC, because in order that when the virtual machine monitor returns using its own SRET, that the program counter value it returns to is the program counter that the guest operating system wanted to return to. So here's a case where very briefly, the real SCPC was set equal to the virtual SCPC. And I'll talk about this in a bit, but the virtual machine monitor also is going to be switching page tables when it goes back into the virtual machine. When the guest user code wants to make then the guest user code, for ordinary instructions, it just executes the machine executes them directly at full speed. When the guest code wants to make a system call, executes the eCall instruction. That causes a trap. That trap goes to the virtual machine monitor in this scheme. The virtual machine monitor says, aha, we're in, consults the virtual mode. The virtual mode is user space. It looks at the instruction that trapped, that faulted. It's an eCall. And then the virtual machine monitor sort of does all the virtual changes, makes all the changes in the virtual state required to simulate a system call trap into the guest operating system. So it's going to set the virtual SEPC to be whatever program counter was the eCall instruction was at. It's going to change the virtual mode back to supervisor. It's going to set the virtual SCAUs to be system call. It's going to set the real EPC to be equal to the virtual STVEC and then call SRET so that it'll jump into the guest operating system's trap handler, which is what, or trampoline page or whatever it is, which is what the virtual STVEC was pointing to. Okay. We have two remaining pieces of business, which are quite important. One is, what about page tables? And the other is, what about devices? So the page table there's two pieces to that. One is that at various points, the guest operating system is going to modify the SATP register. And of course, that'll turn into a trap in the virtual machine monitor, and the virtual machine monitor gets a chance to do something. But what we don't want the virtual machine monitor to do is simply let the guest set the real SATP and then execute after having changed the real SATP, because that would let the guest get at any memory, not just the memory that the virtual machine monitor has allocated to it. So we cannot let the guest operating system simply set the SATP. But we do need to do something to the SATP, because we need to provide the illusion to the guest operating system that, yes, indeed, the page table has been changed. And more than an illusion, when the guest software runs load and store instructions or fetches instructions to execute, we need those to come from the right place, from the place that the guest operating system pointed its page table entries to. So what actually happens when the guest sets the SATP is we can't directly use the guest operating system's page table, but the virtual machine monitor cooks up a new page table that simulates the guest operating system's desired page table. So now the page translation situation is a little bit different. We have the guest, what the guest was trying to set the page table to. So this is the guest page table. Of course, this is the current, the guest kernel. And that maps sort of guest virtual addresses to what I'll call guest physical addresses. And of course, the guest physical addresses are the virtual machine monitor is, given the guest, 32 gigabytes or however much physical memory for its use, presumably starting at telling the guest operating system that its physical addresses start at 0 and go up for 32 megabytes. But of course, they don't in real life. On the real hardware, they're just 32 gigabytes worth of pages somewhere, not contiguous. So we can't directly use the guest's physical addresses because they don't correspond to the real physical addresses. So instead, the VMM is going to maintain a map for each virtual machine that maps guest physical addresses to real physical addresses, what I'll call host physical addresses. So this map is, it's like a page table. It has an entry for every page, every physical page that the guest thinks exists, and indicates what real physical page that guest's physical address refers to, that the VMM has allocated for it. And then when the guest writes a new page table to SATP, in the trap handler for that, the VMM creates what's called a shadow page table, which is going to be what the VMM puts in the real SATP. And this shadow page table is constructed by the combination of these two page tables. And so it maps guest virtual addresses to host physical addresses. And it's constructed by taking every entry in the guest page table, looking at the guest's desired guest physical address, using the VMM map to translate that guest physical address to a real host physical address, and putting that virtual physical pair into the shadow page table. And then the virtual machine monitor sets this to be in SATP as the real page table before returning back to the guest kernel. And so the guest kernel thinks it's set one page table, but actually the real hardware is using this shadow page table instead. And this way, this is what prevents the guest from escaping from the memory it's allowed to use. The shadow page table can only contain host physical addresses that the VMM had allocated for that guest. So there's nothing the guest can put in the page table it asks for that'll allow it to access a page that wasn't allocated to it by the virtual machine monitor. That's a critical piece of the sort of isolation story here. So any questions about the paging setup for trap and emulate?
Sorry, so if the operating system, the guest just wants to make a new process and a new page table for the process, what does it do? Like, what happens?
The guest does the usual, just does exactly what Linux or x86 does right now. It formats up a page table entries to make a page table, and then it executes the instruction to assign that address of the page table into SATP. So that's what the guest operating system does. And but it can't actually assign to SATP because that's a privileged operation. So there's a trap into the virtual machine monitor. The virtual machine monitor inspects the instruction the trap, sees, oh gosh, that guest is trying to assign to SATP. And then the virtual machine monitor would create this new shadow page table from the combination of the page table that the guest was trying to set up. The virtual machine monitor looks at the page table, at all the PTEs in the page table the guest was trying to set up. It translates the physical address in each guest page table entry through this map to get a real physical address, or to cause a real fault if the guest is trying to use a physical address that it's not allowed to. And then the virtual machine monitor installs this shadow page table in the real SATP and returns back to the guest.
Oh, okay, I see. Okay, thank you.
Yes. Okay. Okay, so this shadow page table stuff is certainly one of the tricky aspects of implementing a virtual machine monitor. There's actually another thing that there's another way in which the guest operating system can interact with the page table. The guest operating system may actually, x86 sometimes directly reads and writes page table entries in its page table. And so x86 can modify a page table entry or read the dirty bits, for example, in a page table entry. Now on the RISC-V, if software modifies the page table entry, if you read the RISC-V spec, RISC-V is not required to do anything at that point. So if you modify a page table entry, the RISC-V microprocessor does not promise to immediately observe that modification to a page table entry. It may completely ignore it for the time being. Instead, what the manual says is that if you modify page table entries and you actually want the hardware, the MMU, to see them, you have to execute the svent.vma instruction. And the spec says it's only this instruction that causes the hardware to pay attention to your page table modifications. And so if you're building a virtual machine monitor, your virtual machine monitor on RISC-V can completely ignore the guest modifications to page table entries. But since you know the guest is going to execute an sfence.vma instruction after modifying page table entries, and this is a privileged instruction, you can tell because it starts with S, that's going to trap into the virtual machine monitor. The virtual machine monitor is going to knows that an sfence was executed. It looks at the instruction. It's going to rescan the guest's version of the current page table and look for page table entries that have changed and reflect those changes, if they're legal, into the shadow page table. Execute a real sfence.vma to get the real hardware to pay attention to the shadow page table, and then return to the guest operating system.
So this means that there's only like the MMU actually just uses one page table, right? Which is the shadow. It's not like it's using the EPT or anything. Like the
there's no EPT yet.
Okay, so the guest just like thinks it has a page table, like the GVH or GPA, but that's not actually doing any translation.
Not
and
in
then
this.
the VMM, yeah, makes its own page table based on both of them combined.
That's right. That's right.
Okay.
Just to be clear, the EPT is part of a quite different virtual machine implementation, virtual machine design that requires hardware support. So I'm assuming this is a story about how to build a virtual machine with no special hardware support other than trapping on privileged instructions.
Does this mess up direct mapping in any way?
Well, there won't be a direct map. This will allow the guest, I mean, this will cause the guest kernel to run correctly with what the guest kernel thinks is a direct mapping. But I mean, it's not a direct, it's a direct mapping in the virtual world, but it's not a direct mapping in the, on the real machine. But it doesn't matter because we're tricking we're tricking the guest into everything looks just like it was a direct mapping.
One more question. You may be addressing this later, but I wonder, like when we discussed the trap mechanism earlier in the semester, we mentioned the high performance cost to trapping.
Oh, yeah.
So this sounds like there's way more of a performance hit when we use a VMM.
Yes. There's all these instructions. You know, if your operating system executes a lot of privileged instructions, which it may, and you spend a lot of time in the operating system, then the traps, you may have quite a few traps, and that may cost you quite a bit of performance. And that's what motivates. In a little bit, we'll talk about modern hardware support for virtual machines, which is what today's paper was using. And the high cost of the traps is a lot of the motivation for why Intel felt compelled to, and AMD felt compelled to add hardware support for a much more efficient, or for a virtual machine scheme that had many fewer traps. Yes, that's quite important. But this actually ran, I mean, for many years, this is what people did for virtual machines, and it was very successful, and it works, and it's, you know, somewhat slower, but not so much slower that people didn't like it. People liked it a lot. Okay, any more questions about the trap and emulate strategy for page tables? Okay, let me, as a final piece of the trap and emulate story, let me talk about devices. And so here I'm talking about, you know, an ordinary operating system expects to be able to get at a disk drive to store its file system on, and maybe network interface card, and maybe if it's x86, a UART, so it can talk to its console, and, you know, who knows, a sound card, a graphics adapter, a mouse, a keyboard, all kinds of stuff. So the operating system, we need to, our virtual machine scheme has to have some provision to allow guests to at least trick them into thinking that all these devices that they need really exist. And there's three main strategies that people use. One is just pick some very commonly used device in the class that you need, say a disk drive, and just do an emulation. That is, you're not actually having a real device. The VMM just makes it look like this particular kind of disk drive exists and that the guest is talking to it. And the way you would drive this emulation, typically the guest operating system is going to try to talk to the device through memory mapped control registers. So this is how x86 talks to its UART, the serial port, the console device that you type characters to and that displays characters to you. x86 is talking to some control registers that are mapped, that it assumes the hardware has mapped in a known address in the kernel's address space. And so the way you'd emulate that in a virtual machine monitor is you'd actually not map those pages in the guest. Instead, you would have those pages be invalid, so that every time the guest operating system tried to use the UART hardware or whatever device hardware, the virtual machine monitor will get a trap. And the virtual machine monitor will get a look at the instructions and say, oh, it's trying to send a character on the UART or read from the disk or who knows what. And the virtual machine monitor would have some simulation of a disk or simulation of a serial device, and sort of invoke its simulation to figure out how to respond to the guest's instruction, and then allow the guest to resume. And so this is basically how QEMU implements the UART console device that x86 uses. It just has there's actually no physical serial port in sight, but QEMU emulates one to keep x86 happy. And so this is a common strategy. It's can be very low performance though, because it involves a trap into the operating system for every interaction between the guest and the device hardware. But for low speed stuff, it's works pretty well. A second strategy that's often used, and actually, but if your goal is to be able to boot operating systems that have no idea they're running on a virtual machine, this is pretty much the way you have to go. There's really no other choice. But in the modern world, it's often the case that the operating systems are aware that they're actually running, at a low level at least, aware that they're running on top of a virtual machine. And so a different strategy is to provide virtual devices, that is, not try to emulate a real device, but cook up a device interface that is particularly efficient for the, provides efficient ways for the device driver in the guest to be able to talk to the device support inside the virtual machine monitor. And so you might not have memory map control registers. Instead, you might have sort of a queue of command structures in memory in which the guest operating system would write its commands to the device. And in fact, x86 also uses one of these. If you look at the x86 virt.io disk, virt.io disk.c, you'll see the guest end of a device driver intended to talk to a disk virtual device that's implemented by QEMU. And it uses either little or almost not, either little or no memory map control registers, and so it doesn't really rely on traps, and instead it formats up this sort of queue of commands in memory, as I mentioned. And then QEMU looks at these commands in memory and applies them not to a real disk, but to a file. Like for us, it's fs.image. QEMU applies these commands to fs.image instead of using a real piece of device hardware. So this is another strategy. And a third strategy that people use, so this is higher performance than straight emulation, because you can design the interface so it doesn't require a lot of traps. A final strategy people use is pass-through of a real device. And the sort of classic situation for this is network interface controllers, that provide access to the network. And modern network devices actually have hardware support for talking to multiple guest operating systems running under a virtual machine monitor. And so you can configure a modern NIC to actually act as if it's multiple independent, apparently independent NICs, one for each guest operating system. And then the guest operating system can talk directly, can be configured by the virtual machine monitor so that it's allowed to talk directly to its sort of slice of the NIC, the network interface card hardware with very high efficiency. So this is the modern high performance way. And the guest operating system probably, in theory, I think you could set this up so the guest operating system wasn't really aware that anything odd was going on. But I think in practice, the guest operating system device drivers kind of know that they're talking to one of these special network interface cards. All right, so so these are the options for devices. In fact, I believe that most of the difficulty in implementing a virtual machine monitor today comes in the form of trying to cook up device emulations and device drivers that are sufficiently good that they'll actually work correctly with real guest operating systems. This is where probably the majority of the work is, particularly if you need to use this emulation strategy. Any questions about devices?
So
Okay.
what exactly is, I didn't quite get the difference between the virtual and the emulation, because they're
similar. They're similar. Here's a way to think about it. If you're booting an operating system that has no idea about virtual machines, then it probably has a lot of disk drivers in it, but they're all for real hardware that you can go out and, like, physical chunks of hardware that you can go out and buy. And that means that if you want to boot that kind of operating system on your virtual machine, you need to have an exact emulation. You need to choose one of those real pieces of hardware and have a precise, super accurate emulation of that hardware. So that and I mean, people totally do that, so that works. However, and that would be fine, except most of these, for real hardware, the device interfaces were not designed, the hardware interfaces were not designed to be efficient with a trap and emulate virtual machine monitor. And so it's very often the case that the real device just requires you to read and write its control registers a lot. But the virtual machine monitor has to get control for every write of a device control register because it's, it needs to emulate it. And that means that every write of a device control register results in a trap into the virtual machine monitor, which costs maybe hundreds of cycles. And that means this is slow, this is inefficient. And so the difference here is that instead of slavishly mimicking a real device, some designer has come up with a device interface that's not implemented by any real piece of hardware, but only implemented by a virtual machine monitor. And it just happens to be designed in a way that doesn't require a lot of traps. Right? Instead of chit-chatting with control registers and expecting the device to respond immediately, which really requires a trap, instead the device driver and the sort of virtual hardware are decoupled and don't ever require sort of immediate interaction. Instead,
so in that case, the guest needs its own, like, a new driver. So it's just like the guest will have a driver for like this model of the disk and that model of the disk, and it'll also have a driver for the virtual disk.
Right, and so indeed XV6 does. So at the functionality level, you play this game, maybe you can boot any operating system. Whereas if you play this game, you can only boot operating systems that have been taught about your virtual devices, if you want to use the virtual devices. Turns out this is actually a standard that's provided by multiple different virtual machine schemes. So with this, except for the fact that we never tested it on anything other than QEMU, this disk driver in XV6 might work, or could probably be modified to work on other virtual machines.
So if XV6 was compiled for that board that you showed sometime in the beginning, in that case, it would have to have a different disk driver based on what disk that was running, right?
Yeah, yeah. I think you may be able to buy disk interface, real hardware disk interfaces that now support this interface, but most disk drive don't, and we would have to implement a new, as you said, we'd have to implement a new disk driver for a real piece of hardware. Yes. Okay. Any other questions about devices? All right. Next topic, I want to talk about hardware support for virtual machines. And in particular, Intel's VTX scheme. So what motivated Intel and other hardware providers to add direct hardware support for virtual machines is A, the fact that virtual machine use is pervasive. So a lot of their customers were running a lot of virtual machines. And B, the fact that trap and emulate, as I just described it, often involves a lot of expensive traps. And so it's not particularly efficient. And a third, sort of less interesting perhaps, motivation was that although the RISC-V is pretty well suited to trap and emulate virtualization, the x86, Intel's microprocessor, has a number of detailed features which make it actually very difficult, possible, but very difficult to virtualize. And so Intel was also motivated to try to fix that because so many of its customers wanted to run virtual machine monitors. All right. Okay, so this hardware is, the main point is to make it allow you to build faster virtual machines using this hardware support. And another motivation was to make it easier to implement a virtual machine. And this support has been around for maybe 10 years and is now very, very widely used to build virtual machines. Okay, so the basic strategy is that all that virtual state that in my trap and emulate scheme, all the virtual state that was being maintained by the virtual machine monitor just in software, all that virtual state is going to be implemented in the hardware, in these hardware supported schemes. And that will allow guest software to execute privileged instructions affecting these virtual hardware supported registers directly. So rather than trapping. So the goal is now the guest will be able to execute privilege instructions, but not trap. And the reason, the way that works is that, again, we have a virtual machine monitor and a guest operating system and user level. And the hardware now, we know in the hardware, we have a STVAC and all those, hardware registers. And there's all when we're running in these new schemes, hardware supported schemes, when we're running the virtual machine monitor, we just use the real versions of these registers. But the hardware, when the virtual machine monitor tells the hardware, look, please switch into guest mode, the hardware has a complete separate set of registers dedicated for use in guest mode. So the guest mode can read and write these registers, but it's not, it's reading and writing its hardware copies of its versions of these registers rather than the real registers. And the hardware has, has some kind of extra checks it makes on what the guest operating system can do to make sure that it can't abuse these registers to escape from the virtual machine. But this is most of the basic strategy. And in the terminology of these hardware supported virtual machine schemes, the name, at least in the Intel one, the name for guest mode is non-root. And the name for host mode, where we're using the real registers, is root. And so there's a set of non-root or virtual registers for the virtual machine to use, and there's a set of registers that are used when we're in root mode. So now when we're running in the guest kernel, it can execute any privileged instruction without trapping. So if it wants to read or write the STVEC, the hardware just lets it read or write the non-root copy of the hardware STVEC register. And so all this stuff proceeds at full speed without having to trap it into the VMM. So it's much faster for code that was incurring a lot of traps. You still have to, there's a whole bunch of stuff having involved in configuring this. When the virtual machine monitor wants to create a new virtual machine, it actually has to tell the hardware. And so there is, down in the virtual machine monitor's memory, there's this structure that the virtual machine monitor and the VTX hardware used to communicate, which is called the VMCS or VM control something structure. And when the virtual machine monitor wants to create a new virtual machine, it creates one of these in memory and fills in a bunch of configuration flags and also initial values for all these registers, and then tells the VTX hardware, look, I want to start running a new virtual machine, and here's the initial state. And so there's these new instructions, which the paper mentions. There's VM launch. It's like a new machine instruction, which you tell it the address of this, and it starts running, starting with these registers, like starts running the guest kernel. And there's also this VM resume, because sometimes you break out of the kernel, trap out of the kernel into the VMM, and you need to resume it. And then code up here can run a new instruction called VM call, which sort of intentionally exits from non-root mode and basically traps into the virtual machine monitor in root mode. All right, so when the virtual machine monitor executes one of these instructions to jump into a guest, the ways that it may come back, the guest now can execute ordinary privileged instructions without trapping, but there's a bunch of reasons why you may nevertheless return to the virtual machine mode. One is an intentional exit, but also if a device interrupt goes off, like the timer interrupt goes off, the microprocessor will force a trap out of non-root mode, out of the guest, into root mode in the virtual machine monitor. So in general, device interrupts trap back into the virtual machine monitor. And so that means that a guest operating system can't hog the CPU. Every time the hardware timer ticks, the virtual machine monitor gets control. And if there's multiple guests, it can now sort of basically time share the machine using the timer interrupts among all the different guests. Okay, so this is the basic strategy. Basically, there's a second set of registers. The other big piece of machinery that VTX provides is a page table support. We're operating up here in the guest world. We still need a page table. Now we need a page table for two reasons. One is the guest kernel wants to be able to configure its own page tables. Wants to be able to load CR3, which is the Intel equivalent of the SAT-P register. So we'd love to be able to, or VTX allows the guest kernel to load any value it likes into the CR3 register to set the page table. And the hardware will actually obey that page table that the guest kernel loads. But we know that can't be which is fantastic, right? Because now the guest kernel can load a page table without trapping the VMM. But we know that we can't just let the guest kernel put anything it likes in its page table because that would allow it to read and write arbitrary memory. So this VTX scheme actually has another important register, which is in fact part of the sort of real, well, who knows where I should draw it, but I'll draw it right here. The extended page table register, and the virtual machine, which points to a page table, right? That maps one kind of address to another kind of address. And the virtual machine monitor sets, when it's about to run a guest kernel, it sets up an EPT for that kernel, tells the hardware, look, here's the EPT for the virtual machine I'm about to run, and then jumps into the virtual machine. And then the game is that the MMU on this machine, when it's translating a guest virtual address, it first translates the guest virtual address to a guest physical address to the page table that the guest sets up, and then does another translation of that guest physical address to the EPT to get a host physical address. And the hardware does that automatically for every memory reference the guest does. Does this double level of translation. And so this again gives the VMM control over what physical memory the guest is allowed to use. The guest can set up any page table it likes and can do it quite efficiently because it can directly execute the instructions, but it's still constrained by the EPT, which the VMM configures to be able to only use physical pages that the VMM wants to let it use. Any questions about the EPT?
Oh, sorry, I have a question not about the EPT, but about the second set of registers. So if you have 2 cores and you want to run 2 VMMs, do you get like a third copy of the registers?
Oh, every core has its own set of these registers. Every core has a sort of independent, an independent instance of all this VTX hardware. So every core has its own 32 general purpose registers, its own real control registers, and its own virtual registers for guest mode.
Okay.
And its own EPT. So you can be running 2 different guests on 2 different cores. They all have their own. Every register, every core has its own one.
So you need a new VMM too?
Well, I mean, it could just like an ordinary operating system. Like XV6 can support multiple processes, and it's all the same XV6. But although, and just like XV6 has a separate struct proc for every process, our virtual machine monitor would have a separate struct VM or whatever it is, one for each guest to keep track of that guest information for that guest.
Okay, I see. Thank you.
Yes. And as I mentioned before, the switching, if you have 1 core and 3 guests, the switching can be driven by timer interrupts, which go to the virtual machine monitor, not the guest. Okay. More questions about virtual machines before I switch to the paper. All right. The paper takes this hardware as a starting point and uses it for something else, not a virtual machine. So that's a lot of the interest in the papers, that they took this hardware, which is like absolutely designed just for virtual machines, and the paper saying, gosh, we could just use this hardware to do something that's not a virtual machine. What their sort of high-level view of what they're doing is they want to implement the ordinary processes. So now we're back in just Linux, no virtual machines anymore, just Linux, but assuming VTX hardware. So this is Dune. We have Linux, and we've loaded the Dune loadable kernel module into Linux. So now this Dune software is running in supervisor mode as part of the Linux kernel. But for the most part, we're running Linux, and we're expecting to run Linux processes. So the abstraction we're trying to support is mostly the process abstraction with system calls and all the sort of ordinary things that Linux processes can do. But we want to use this VTX hardware to give sort of more, sort of allow ordinary processes to do some extra things. And there's really, so we're actually going to run, so Dune runs these processes, or allows a process to switch into Dune mode, which means that instead of just being protected, being isolated by a page table, now this process is isolated by the complete VTX apparatus. So for this process, Dune's going to maintain, this process now has this virtual set of all the control registers, like its own CR3, and therefore its own page table, because this process is going to run in non-root supervisor mode, so it can run all the privileged instructions, although against the virtual state implemented by VTX. So one of the critical things this process can do under Dune is set up its own page table using its own hardware CR3. And of course, Dune, controls an EPT for this process. So, and the EPT is going to be set up to only have entries for this process's ordinary process memory. So the process can put anything it likes in CR3, but because the MMU translates through the EPT after translating through the ordinary page table, the process still cannot escape its allocated memory. So the process doesn't have any sort of additional powers with respect to other processes or kernel memory. It just has now a more flexible way of setting up its own memory. All right, so one thing a Dune process can do is have its own page table. In fact, it's basically required to have its own page table because otherwise it won't work. And the other thing a process can do is have supervisor mode and user mode within its little virtual machine, and be able to have the supervisor code set itself up to be protected against the code that it runs in guest user mode. So the paper really talks about these two different uses, two different things you can do with Dune. So this ability to get at, for a process to get at the hardware support for supervisor versus user mode allows them to run untrusted plugin code here in a sandbox. And so the idea is, oh, maybe maybe the main program is like a web browser. You can download download plugins that your web browser runs. Maybe a new video decoder or a new ad blocker or something, but we don't totally trust that plugin, so we'd like to run it with restricted privileges somehow. It's possible, but a little bit tricky to do in ordinary Linux. But with Dune, we can run the plugin up here in user space, and the web browser, which runs in the process in supervisor mode, can configure the page table, can configure a different page table for use by this user code because it's allowed to write CR3. And that can allow it to run this untrusted plugin code with only allowing it restricted access to just some pages of the web browser's memory. So that even if the plugin code is malicious, it can't just arbitrarily read and write the main web browser's memory. And if the user code, the user code may be expecting to make system calls, but those system calls actually trap into the supervisor mode of the process and not into Linux. So this plugin code may think it's calling fork or read or write or who knows what, but actually those attempts to execute system calls trap into the web browser in the process, and it can do whatever it likes. It can not do the system call or execute the system call or who knows what. So now our web browser has sort of full control over the sandboxed plugin code. As a quick overview, any questions about using Dune to sandbox? And to be fair, this is an effect that could be achieved by quite different techniques using existing Linux facilities, but Dune allows you to provide it in a particularly kind of elegant and efficient way by using the VTX hardware. The other thing that the paper talks about using Dune for is to make garbage collection faster. And here it's the way it does that is by allowing the garbage collect. So we're not doing sandbox anymore. We're actually not even using user mode. We're just having one program. We're assuming that we're writing just whatever program, who knows what, but in a garbage collected language like Java or Python or something. Garbage collection can be slow. There's dozens and dozens of tricks for making garbage collection faster. But one of the things that's important in garbage collectors is the garbage collector many garbage collectors trace find the memory that's still alive, that's still active, by just tracing all the pointers through all objects, starting at the registers. And if it doesn't find some object after it's completed the trace, then that object can't be reached, isn't referred to by any pointer, and can be freed. But many garbage collectors run at the same time as in a different thread or something as the main program. And so maybe the garbage collector has started tracing pointers from, maybe from some set of registers, and has followed a pointer to this object, which had pointers to these objects. And the garbage collector is following each of these pointers down to the tree or graph of objects. And maybe the garbage collector has gotten, down here so far, and actually trace through all these objects. But then, because the garbage collector is running concurrently with the program itself, maybe the program modifies this object that the garbage collector's already traced through. So that's a bad deal, because now the list of object pointers the garbage collector has decided are live or dead or whatever may not be correct, because some object it's already seen has been modified by the program. So Dune, using page table support, provides a way for the garbage collector to detect writes like that. And in particular, Dune sets up the CR3, the virtual CR3 supported by VTX, to point to its own page table. And it leaves all these page table entries valid, but it looks at the D bit. Every page table entry has a dirty bit that indicates that there's been a write to that page. So if the program writes some object, then the dirty bit in the corresponding page, in the page table, the dirty bit will be set. And so when the garbage collector is finished tracing through the objects, it goes back and looks at the D bits in the page table to find all pages that contain objects that might have been modified, and rescans those objects. And it turns out that this facility of getting at the D bits is difficult and slow with ordinary Linux. I don't even know if Linux supports it. There are operating systems where you can make system calls to ask for D bits. But if you use Dune and VTX, then the process can just use ordinary load and store instructions to get at the PTEs and therefore the D bits, and it's very fast. And so they showed, that this makes this trick for some programs that are, garbage collection intensive, makes the programs significantly faster. Any questions?
What would happen if the sandboxed program wants to run its own garbage collector or something? Would that?
I see. So you were sort of using, all right. So we got, we're using Dune. We have a Dune process that's actually using VTX's supervisor versus user mode. We're running a plugin up here in user mode, and the plugin it's also written in a garbage collected language and was like to have its own page table, its own CR3 pointing to its own page table with its own D bits. So no, that doesn't work because we're going to run the way Dune wants you to run plugins, sandbox plugins, is to run them in guest user mode. Guest user mode is not allowed. It's just like user mode. It's not allowed to think about CR3. And so in guest user mode, we don't get to have our own page table. And so we don't get quick access to the D bits. It's only in guest supervisor mode that we can have our own CR3. So you can't, there's no obvious way to combine the two kinds of tricks that Dune allows.
What about, let's say somebody wrote a browser actually using Dune? That would mean that would be quite tough to make if some computers didn't support Dune or something, right? It's hard to just put Chrome into to use Dune if not everyone has that kernel module.
Right. So first of all, you have to be running on a computer that supports the VTX. The underlying computer has to support VTX, which means many Intel chips, So you need VTX to run Dune, and Dune had to be loaded in order to run the browser that takes advantage of Dune. So yeah, you got to set all this up correctly. I mean, it's a research project. It's intended to sort of get people thinking about things that could be deployed in the real world if it seemed like they were valuable enough. So, and just like Linux, I mean, Linux has hundreds and hundreds of features it has, and so if somebody decided to add Dune to Linux, as a standard feature, then you could start relying on it, and Chrome could just use it, and it would not be a problem. But that.
Sorry, so in a high level, Dune is like making a VM, but instead of a VM, you run a process.
Or yeah, I mean, you can phrase it either way. It's supporting what's mostly a process abstraction, but it's using, instead of using the page table hardware, it's using the CPU hardware to support a process abstraction. But the particular CPU hardware it's using is the VTX hardware, which has a few extra features, like the ability to set up your own page.
Right. I see. I remember in the paper I read process level abstraction, but I didn't understand what that means. But now I understand it. Thank you.
Good. All right. Time is up, and I'm happy to continue. If anybody has any more questions, I'm happy to answer.
Yeah, so I had a question in particular about something that said in the paper was if a Dune, like a process inside Dune forks, it becomes a non-Dune process. Isn't that like a security flaw in a way? Or
what's the attack?
Well, you've run something as a Dune process thinking that it's now safe, but then it can just fork to escape.
So here's the possibility. Yeah. Okay, so if let's see, code down here in supervisor mode, there's no security problem for this, with respect to this code, because it already had whatever privileges were possible. It does not going to gain any extra privileges by forking, right?
Okay.
Code up, but maybe it's using Dune to sandbox a plugin, and we have untrusted code up here that it would be dangerous to, let it run without Dune, because it's not trusted, and we're using Dune to sandbox it. And so then if we forked, okay, so this code cannot fork, right? It can try to call the fork system call, but
I see.
a system call instruction up here traps into the supervisor part of this process, and presumably the supervisor part of this process is carefully written not to be tricked, and so it's not actually going to fork. So that doesn't work. If the supervisor code, it is allowed to fork. It is allowed to make Linux system calls. It'll get a fork of this process with the same memory image. So we'll get the plugin up here. And
I see.
If it didn't realize that fork turned off Dune, and it did, well, I mean, it's hard to see how this could actually happen. But if it did something to resume execution of the plugin now, that would be very foolish, because now the plugin's not sandbox. In fact,
I see.
This, the code to jump it in the sandbox here involves privileged instructions, just like it does on RISC-V, because it switches guest modes. And if you execute that instruction here, that's an illegal instruction. So instead of jumping,
I guess what I was misunderstanding was, I think that the plugin is not a process. Like the Dune process is the sandbox. The plugin is just inside there. The Dune process is just enabled to use features to let the plugin run faster, basically.
That's right. And we're absolutely assuming that this software down here is clever, is careful about what it lets, about preventing, the sandbox from actually calling fork in real life.
And it's not unsafe for the Dune process to have supervisor mode, because it's actually supervisor mode in non-root mode, which is the same as supervisor mode in a guest OS, right?
That's
right. So it's like you can let it do everything, but because of VTX, it's gonna be like a virtual machine, so it's not gonna hurt us.
That's right. It can't escape from its address space, because EPT is Dune has set up EPT to constrain it to its address space.
That makes sense. So one last thing I had, there was like a paragraph on EPTs, and it said that the user page table can just expand the addresses, like remap them to their original layout. That was something I just didn't understand the whole paragraph.
So I don't completely understand.
But maybe that's a bit specific.
I think what's going on is that the physical addresses are on the x86 have fewer bits than virtual addresses. So I'm kind of guessing. And so that means that the EPT, you know, the ordinary page table maps virtual addresses to physical addresses. The physical addresses have fewer bits. And so that constricts that means that when Dune is setting up an address space for a process, or one way to look at it is when Dune's setting up the address space for a process, the process address space has to fit in the smaller number of bits for a Dune process.
Okay.
Regular processes can maybe use, I don't know what the numbers are, let's say 48-bit virtual addresses, but maybe physical addresses are only 36 bits. Again, I'm making this up.
Okay.
An ordinary process could use all 48 bits for virtual addresses. A Dune process can only use 36 or whatever. So there's like different rules for things have to fit down.
Okay.
I had a question about the VTX scheme and how we're accessing page tables. So
Yes.
When, like, in the way we're accessing page tables, because we're going to the EPT and then like doing the second layer of translation there from the guest physical address to the host physical address, is the latency of accesses to the page table actually lower?
It takes more time. Potentially takes more time, possibly
Okay.
much more time for the hardware MMU to translate an address. Because now it has to do two, well, the worst case is very much worse because, you know, on the RISC-V, there's multiple levels of the page table. And so the MMU has to read an entry from this page table page and then next and the next. Each of those, the x86 also has multiple levels. And so in the x86, in the lookup in the main page table also has to make multiple memory references potentially. Each of those multiple memory references has to go through the EPT. And the EPT is also a multi-level page table. And so I don't even know what the worst case number of memory references is, but it's quite a bit worse under VTX than it is with a than it is in the ordinary case. So there's a potential there. And you know, in fact, there's lots of caching. And so usually you don't run up against that worst case, but.
Okay. And so virtual machines, are they still like generally slow today? And if so, I guess I was wondering, how does AWS work if it seems to be fast and it seems to be working well? So
my belief is that they use VTX hardware, that they use the support that we're talking about, and that it is as well as clever device schemes for efficient device access. And that the result is that AWS virtual machines are like fast or not much slower than a real computer.
Cool. Thank you so much.
Yes.
Oh, I had also another question on the shadow copy for Trap and Emulate. So you said that it like, I understand how you would make it, but does it actually make the shadow copy, or does it just, I think it has to make the shadow copy, right? Because it has to allow the process just to do it itself, not like to go through all of the traps, but does it do it every time? Does it remember the previous version?
Well, okay, yeah. So yeah, yes and yes. The virtual machine monitor has to create a new page table, or there, you know, yes, has to create a new page table, and it's the virtual machine monitor's, you know, page table which it formatted up, which is what the real hardware uses. Now, of course, there are plenty of opportunities for caching and for reuse. So if the and the clever virtual machine monitors, if they notice that, oh, the guest changed just one PTE, then the virtual machine monitor may be able to do correspondingly limited amount of work to update its shadow page table. And it also may keep you know, if it's sort of multiplexing time sharing among multiple virtual machines, the virtual machine monitor will keep around the shadow page tables for the virtual machines that aren't running, so that it can reuse them directly when it switches back to that virtual machine.
Okay, I see. So does that mean that you have to remember a shadow copy for like each process for each virtual machine?
Yes, there are many, right, there are many page tables running around in the virtual machine. The virtual machine
that's
is
tricky.
aware of all page table switches that the guest does. Yeah, it's
Okay.
the specific issue of maintaining the shadow page tables has consumed a lot of work by
Right,
people who
right.
make
That seems a
virtual
little
machines.
tricky. Thank you so
Yeah,
much.
in the days before, you know, and this is one of the many things that hardware supported virtual machines made quite a bit easier.
Oh, okay, I see. Okay.
Because the
Thank you so
EPT
much.
means you don't have to cook up your own shadow page table.
Right. Yeah, that's nice. Yeah. Thank you.
Yes.
All right, gotta head out, but I'll see you guys
All right.
on Wednesday.
Yes.
Thank you.
Thank you. Bye-bye.
Thank you.
Is it okay if you have time for one more question?
Yes, please.
Um, this one is about the garbage collection, how it like rescans to see if like they're dirty bits. Like, is this like a sort of a continued process where like it continues to rescan like indefinitely because couldn't?
You're asking, oh yeah, would it ever terminate? Supposing that, oh, there's always something new modified. So in fact, potential problem. In fact, what the garbage collector does is it does one pass through to completion, and then it freezes everything else but the garbage collector, so nothing else can happen. Then it goes back and look at the dirty pages, but of course everything else is frozen, and so no more dirty pages can occur. And then the garbage looks at all the dirty pages, and then it knows it's done. It, you know, does whatever it's supposed to do to finish up and create the free list, and then it resumes all the threads that it stopped.
Oh, okay, yeah, okay, that makes a lot more sense. I know it froze and everything else, but
yeah, this is complex stuff, and of course, there's not enough room in the Dune paper to explain all the ins and outs of what the garbage collectors have to, sadly.
All right, yeah, thank you so much.
Thank you. See you later.